we're talking about a three-phase system. So a three-phase source might have a delta connection or Y connection. Okay, it's a Y connection and delta connection. So this Y connection mostly is going to be connected to, Y or delta, a three-phase. This three-phase is going to be connected to a three-phase load. Can I connect this three-phase system to a single-phase load? Yeah, it is possible. You can connect a three-phase system to a single-phase load, but at the same time, make sure we connect something to each phase. So load 1, ground it, load 2, ground it, and load 3, ground it. Okay, these are the individual loads. We can connect them and ground them. But the disadvantage with this, what if these two are all these three loads are different amounts of loads. Each load is drawing different amount of power. That's called unbalanced load. So if it is unbalanced load, basically there is some current is going to pass through the neutral, so we are wasting energy. So running a three-phase system on unbalanced load is not a good idea. So in this subject, in this video, I'm going to talk about only balanced load. Okay, so if you have a source, three-phase source Y or delta, and three-phase load is also Y or delta. So source is Y or delta, load is Y or delta, then we'll end up with 4 combinations. So a source might be Y, load might be Y, so YY connection. This is called YY connection. Okay, and Y delta, delta Y, and delta delta. These are the 4 types of connections we'll see in a three-phase system. Okay, so here this is a source and this is a load. Now I'm going to solve an example in this video, a YY connection. So YY connection is nothing but Y source and Y load. Here is an example. In this example, he's talking about a three-phase 208 volt Y connected source is connected to a Y connected balanced load. So source, he's saying Y connected, and load is also Y connected. Important point, whenever you see this number, this is always line value, line voltage. Okay, in three-phase system, the given voltage is always a line voltage. Now he's talking about it's a balanced load. Impedance on each branch is 8 plus j6 ohm. Find the active power, reactive power, apparent power conjugated by the load. Also find the line current and load power factor. So I always prefer to draw the diagram, circuit diagram, and I always follow positive phase sequence. Those things usually don't mention in the question. Okay, so here is a YY connection or star-star connection. So A, source side always use the capital letters, load side I always use small letters, A, B, C. I'm using positive phase sequence, so always walk in the clockwise direction. Make sure you connect A to A. Sometimes you may get confused and connect B to C, but make sure you connect B to B and C to C. Okay, so here this is 8 plus j6. So each branch has the same value. Okay, now he gave us this voltage as 208 volt. Okay, VAB. Okay, it's always line to line voltage. The given value is always line to line voltage. Now what we can find without calculating anything here, the first thing we can find is power factor, load power factor. The load power factor equal to cos theta L. I'm going to take that as load. Here I don't have any impedance on this line. Sometimes you will see some impedance on this line, right there. Those line impedance represents the transmission line impedance, because most of the cases, say for example our university, which consumes approximately around 10 to 12 megawatts of power. on average. Okay, so the 12 megawatt power has to come from nearby power plant. And most of it is going to come from the nearby, but need not to be 100% is coming from the nearby power plant. But assume that it is coming from nearby power plant, which is 15-20 miles away from our university. So those 15 miles we're running a wire. That wire is going to have some resistance as well as reactance. So that's what we're going to represent here as a line impedance. So in this example, we don't have that. If we have that, then you're going to have cos theta L and cos theta S. So cos theta S indicates the source power factor. So in this case, source power factor and load power factor, both of them are same. Next example, I will solve an example with line impedance. So here it's R over Z. Since it is a balanced load, one power factor is good enough. 8 over square root of 8 square plus 6 square. So 8 over 10, this is 0.8. Okay, whenever you see power factor, you must indicate whether it is lagging power factor or leading power factor. So 8 plus J6, this plus indicates this is resistive load, this is inductive load, okay, or inductive reactance. So whenever you have inductive load, that is lagging power factor, because if it is inductive load, V goes first, current always lagging. That's what that lagging indicates. Okay, that this theta and this theta, they both of them are same. Okay, so we found the load power factor. Now we'll find the current. Before finding power, I'm going to find the current. So to find the current, I need to use, I can find IPH if I know the VPH. Okay, voltage per phase. Okay, here most of the cases this neutral is going to be grounded. The neutral here is also going to be grounded. Okay, so VPH equal to VL over square root 3. I'm going to take only magnitude. I'm not going to worry about the phase angles in this case. 208 over square root 3, I will leave it approximately 1. This value is 120.088. I can take that as 120.1 volt. Okay, that's the phase value. As I mentioned, I'm not worried about the phase angles. That's my VPH. Now my IPH is the current passing through the phase. IPH equal to VPH over impedance per phase, which is 120.1 divided by impedance is, I can say, 10 at an angle of, when you convert this, so Z equal to 8 plus J6, when you convert this into polar format, you will end up with 10 at an angle of 36.86. Okay, 10 at an angle of 36.86. So 120 over 10, which is 12.01 at an angle of minus 36.86 ampere. Okay, so that is the current. Here in three-phase system, even you don't need to worry about this angle. I'm going to take the magnitude only. Now the power formula, before finding power, we'll find the line current. So it's a star connection load and star connection source too. But anyway, I found this current IPH. Once I know that current, can I find IL? In this case, my IL and IPH aren't the same. So IL must be equal to IPH, which is 12.01 ampere at an angle of minus 36.86. But I'm not too keen about that phase angle. If needed, you can put it there. It's not going to bother us. 36.86. Now P equal to 3 times VPH IPH cos theta, which is load power conjugated by the load. We know VPH 120.1, we know IPH 12.01, we know cos theta, which is 0.8. That will give you, this value is 3461.76 watt. That's the active power conjugated by load, conjugated by the load. QL is the reactive power, 3 times VPH IPH sin theta. So we know cos theta cos theta equal to 0.8. Based on this, we found theta value, which is cos inverse of 0.8. We end up with 36.86 degrees. So sin theta is nothing but sin 36.86. That will give us 0.6. So 3 times 120.1 times 12.01 times 0.6. By the way, you can use another formula, square root for power, or active power or reactive power, which is square root times 3 VL IL cos theta. You can use this formula. Same thing here, square root 3 VL IL sin theta. Okay, so this value is 2596.32 volt ampere reactor. So I have active power and reactive power. So the apparent power S equal to P plus or minus JQ, but in this case plus JQ, because what kind of load is this? It is a resistive load. Resistive load always consumes the active power, and inductive load also always consumes the reactive power. Okay, so both of them are consuming, so both of them are taking power. So it is 3461.76 plus J 2596.32 volt ampere. That's S value. This is what he's asking in this video. This is called complex power, S value, or if you want apparent power, square root of P square plus Q square. Both of them are same. This is called complex power. This is called apparent power. Okay, so apparent power equal to square root of 4327.2 volt ampere. Okay, by the way, either P, Q or S, they will not have any angles. Okay, if you are indicating angle, that's wrong. Power is a real number, reactive power is a complex number, I mean imaginary number, and apparent power is a complex number. Okay, I will stop this video here. I will solve more examples in the next video. Thank you.